Hello guys, and welcome to our last lecture this week, which is called Quantum Ensembles. Previously, we already started using some elements of quantum mechanics to describe quantum system, but now we would like to take it to a more serious level and to actually understand the behavior of quantum statistics. And to do that, let me remind you. First, fundamental difference between classical and quantum mechanics. The difference is that in classical mechanics, we use real numbers. So, say coordinates and moment of particles, they are always real. But in quantum mechanics, the main object is the wave function, which is a complex number. And we can split this complex number into its amplitude and its phase, shown here as phi. And there is no classical analog of the phase in classical mechanics. Observables in quantum mechanics are probabilities or squared moduli of amplitudes, and they are positive real numbers. However, phases lead to quantum interference between states, and I will talk a bit about this a bit later. So, a statistical ensemble in quantum mechanics is a collection of states of the system, which, as in classical mechanics, if we look at it as a statistical ensemble, then these states, quantum states, should be completely independent of each other. Therefore, we must require that there should be no quantum interference among members of this ensemble. So, consider a system interacting with an environment, a heat reservoir. So this system is described by some Hamiltonian, and there is also a large Hamiltonian which describe a system plus a reservoir. And there is this big psi, which is the eigenfunction of the system plus reservoir, which depends on the coordinates of the system, coordinates of the reservoir, and time. So this is the big guy who describe the whole system altogether. Now let's denote H to be the Hamiltonian of our system. And we assume that its eigenfunctions, little psi n of x, are orthogonal and normalized. And moreover, they form a complete set, all functions in the Hilbert space, or in the infinite dimensional vector space of quadratic, of square integrable functions. A complete means that any other function can be decomposed as a linear combinations of these functions. So these functions are eigenfunctions of this Hamiltonian with the energy levels En, and they are orthogonal. So if you integrate them, it's complex conjugate with another one. This is a scalar product between two eigenfunctions. Unless m equal n, it's 0. When it's m equal n, the same eigenfunction, it's normalized to 1. Being a complete set of eigenfunctions, we can expand our big eigenfunction of system plus environment in this, okay, as a linear superposition of this little eigenfunction. So we can always write the expansion like that. So here is the sum over all eigenfunctions of our little system. And as a rule, this sum is infinite. And coefficients, they may depend on the coordinates of the environment and time. They do not obviously depend on the coordinates of the system, because coordinates of the system is system coordinates that are contained in the eigenfunctions psi n of n. Okay, quantum interference I mentioned before. It occurs because psi represents not a probability, but a probability amplitude. To find a probability, or to be more exact, probability density of finding the system at position x and coordinates x of the environment, we need to take the squared modulus of this guy. This will be a probability density. And when we take a squared modulus, we need to multiply psi star by psi. And this will result in taking multiplying these two sums. One is complex conjugate by another one. So the result will be a double sum over mn, and we will have here cm star complex conjugate cn psi m star complex conjugate psi n. Okay. Now these big eigenfunctions should be normalized. It means that if we integrate it over coordinates of the system and over coordinates of the environment, then it should be 1. If you plug it in here and then the integral over the coordinates of the system of these two products due to orthogonality, it will be always 0 unless m equal n. And when m equal n, that will be 1. So integrating over the coordinate of the system, we can get sum over m. The only contribution will be from diagonal terms, m equal to n, and so it will be sum over n, integral over coordinate of the environments of these coefficients of expansion. And it should be 1. Okay? Now, these coefficients Cn are obviously complex numbers. So let's write them in the polar coordinates as their amplitudes times their phases, exponential of their phase. And if we plug it in here, we get the product of modulus of these two coefficients. And here we will get exponential of phi n, because of complex conjugate, minus phi m. And as you can see, psi n and m, they describe eigenfunctions of our system. And there will be some terms coming from interactions for different m and n, because these exponents, this non-diagonal term may happen in this sum, and they will describe this quantum interference, which is not a desirable feature, because we expect that states in our quantum ensemble should be statistically independent of each other. So they should not interact in any way. Okay, so this is not good from the point of view of statistical mechanics. Now, let's look at this expression again. These phases, they basically describe interaction of our system with the environment. Okay, if these relative phases can be regarded as random numbers, then the interference will vanish on average, because if we average it over a macroscopically large period of time, then if they are described by some random numbers, then this non-diagonal term will basically, fast oscillating terms, will if we integrate over the over some period of time, then all non-diagonal terms will disappear. In that case, psi describes an incoherent superposition of pure state. Okay, and in that case, such superposition will indeed define a quantum ensemble. So for an environment with many degrees of freedom, comparing to the system, this relative phases will be an extremely sensitive function of the environment coordinates and will fluctuate very rapidly with time. It changes very rapidly even in response to very small changes of the environment and time. Okay? So on average, it will become uniformly distributed over the interval from 0 to 2 pi. So if we now calculate the average of this exponent over small intervals in x and t, of course, small, macroscopically small, but these intervals will still have a huge number of oscillations of those exponents. So on average, this average of these exponents will become 0. So as a result, when we average over time and coordinates of the environment, all diagonal terms in this sum will disappear, and then psi of x, xt will becomes an incoherent superposition of states. And this is what we say when we say that it corresponds to a quantum ensemble of the states described by individual pure states psi n of x. Okay? So, as I just explained, these relative phases will not explicitly enter any results. So we want to develop a formalism which allows to avoid them. So let's consider some observable, like energy, in our system, and in quantum mechanics, any expectation value of this observable will be defined by averaging, by taking matrix elements. So if psi is the eigenfunction of our system plus the environment, and O is some observable, then its quantum mechanical expectation is normally calculated as we just take matrix elements of O between two states psi. And here I use the so-called bra and ket notations introduced by Paul Dirac in quantum mechanics. And if I substitute my expression for eigenfunctions psi from the previous slide, what I get, I can write it in the form sum, if I expect my states psi in terms of in this form and substitute this expression, what I get sum over nm, those coefficients cn conjugate cm, and matrix elements of this observable O in between the eigenfunctions of the quantum system. Okay, these numbers O and m, they are given as the integral over the coordinate of the system psi n of x by psi m of x, O of x. This is how we calculate averages, how we calculate matrix elements in quantum mechanics. Okay, now we want to calculate now not these matrix elements at some particular moment of time, but we want to calculate its thermal average, integrating by this expectation value over coordinates of the environment and averaging over time, okay, which is large comparing to microscopic fluctuations of those phases, okay? So instead of looking at this matrix element, we want to integrate it over the coordinates of the environment and then average over the time interval, which is short on a macroscopic scale, but long compared to a relaxation time in the system. Okay? So when we do this average, now we substitute this expression, O is the expectation numbers, and we take out this integral, which is the integral involving those numbers C and Cm, and integral over the coordinates of the environment, and then taking the average over time. Okay? Now here's this formula again. And now let's remember that when we said that the random phases contributing to this coefficient Cn, Cm, those factors exponential of I, phi n minus phi m, they will be very fast oscillating, okay? So they will kill this integral unless n equal to m, okay? And so the only contribution from this integral will come from the terms with n equal m. So this is what's written here. This random phase assumption gives us this integral equal to 0 when n not equal to m. So we obtain that the only diagonal elements will contribute to this sum. Let's denote these numbers rho n to be the integral of dx, those coordinates cn squared, because cn star cn becomes cn squared. So our average now becomes the sum, this is what's written here, sum over diagonal elements, because only n not equal to m contributes, so this sum, but this number rho n, it depends on normalization of those coefficients cn, okay? So if they are not properly normalized, then we need to define our average. So I mentioned something about normalization of the function, but now I say that, okay, if my big eigenfunction is just with some coefficient Cn and I don't normalize it, then I need to replace the average by this sum and divide by the normalization condition. Because if we substitute O equal to be 1, then obviously this will be 1, and the average of the operator 1 of any observable 1 should be just 1. So this is a typical normalization condition, which we already seen when we studied classical ensembles. Okay. In other words, rho n is the relative weight of the pure state psi n in the ensemble, and is the quantum analog of the classical density. Okay, if you look at this formula, it looks very similar to what we had in classical mechanics, but now interpretation is slightly different. It's completely quantum. Okay, so now so we have these numbers rho, in principle infinitely many of them, as many as there are eigenfunctions of our system, and number of eigenfunctions is normally infinite. So we now define a density operator rho with the eigenvalues rho n with respect to this particular basis psi n. In other words, we're saying that if we denote this eigenfunctions psi n and psi m using this bra and ket notation, this notation is basically we apply taking the matrix element of this operator, we multiply it by psi m, psi n conjugate, and integrate over the coordinates of the system. That's the notation of this matrix element. So in this basis, we say that this operator rho is diagonal, okay? Or can be given explicitly by this infinite dimensional matrix. This is what's called the density matrix, rho, with respect to the basis psi n. And this matrix actually carries information about the environment of our little system, okay? Interaction with the environment, because remember, the origin of this matrix came from those coefficients Cn when we expanded our big eigenfunctions in the basis of our little eigenfunction. So this matrix is diagonal, but it's diagonal only with respect to the basis psi n. But we can, in principle, now write down the thermal average in the basis independent form. Because what happens if we choose another basis, not the basis of the eigenfunctions, the standard basis labeling our system? It depends on the system, of course. If it's a discrete system, for example, of spins, that just we can introduce the basis of spins corresponding to the size of the system, but eigenfunction of the system will be much more complicated, and they also give another basis. So I want to write down now the thermal averages in the basis independent form. And it was basically done by this guy, and density matrix was introduced by him. It was John von Neumann, the greatest scientist. And let me tell you a few words about him. He was born in 1903 and died very young, 54 years old. He was born in a very rich family of a Hungarian banker. And he has done major contribution in mathematics, in physics, in computing, programming, economics, statistics, etc. etc. It's all written here. For example, maybe you heard about von Neumann computer architecture, which is basically based all modern computers based on this, on his von Neumann architecture. So in physics, in quantum mechanics, he was made great achievements in operator theory for quantum mechanics, development of cellular automata, and digital computer, and etc. During the Second World War, he worked on Manhattan Project and solving key steps in the nuclear physics involving thermonuclear reactions and the hydrogen bomb. He was quite an amazing child. His father believed that all children should speak very many languages, so he was educated in 5 languages when he was a child. So he could fluently speak 5 languages. So he was a child prodigy, and when he was 6 years old, he could divide 2-digit numbers in 2 8-digit numbers in his head. When he was young, he actually thought that he really liked history, okay, and he was reading a lot. And by the age of 8, he completely studied 46 volumes of a very known Hungarian 46 volumes written by some very known Hungarian historian. And later on, when he worked at the Institute of the Advanced Studies, one of the professors of history there, when he was already about in his 40s, 50s, accepted that von Neumann knew ancient history much better than him. Okay, and for example, another story about him, when once told by his mother when he was 7, he entered the room and saw his mother aimlessly staring at the wall, and he asked her, "Mother, what are you calculating?" So he could not imagine that someone could just stare and aim and just aimlessly stare at something without calculating something in his head. So at the age of 15, he was introduced to Gabor Zego, who was a very famous analyst, and on their first meeting, Zego was so astonished by his talent that he was brought to tears. By the age of 19, he already published 2 major papers, and at the age of 30, he got a lifetime professorship at at Institute for Advanced Study. Unfortunately, he died very young, 54, from cancer. And when he was diagnosed, when he was 53, he couldn't believe it, that all his knowledge he accumulated during his life and all his achievements could just simply disappear. He couldn't accept it in the final year of his life, but nothing we could do about that. So he was a great guy. Okay, so density matrix. So this is an average. Let's look at this again. So we remember that this is matrix elements of our observable, diagonal matrix elements, and this we represent it as some kind of diagonal matrix. So we can write it in the form, because this matrix is diagonal, we can write as a diagonal matrix times matrix O, and then taking its trace. Okay, so if when we multiply two matrices, it's take its trace, that will be exactly the expression. So it's like, because this matrix is diagonal, and so we multiply it by diagonal elements O and taking trace, this will be just trace of row O. And then the sum of rows, it will be just trace of the matrix, sum of diagonal elements of the matrix. Okay, so this is a nice looking expression, but what's important, that it's actually basis independent. Remember that the matrix rho is diagonal only on the basis of eigenfunction. Now I claim that if we change to another orthogonal and normalized basis, then this expression will not change. Okay, and then a simple demonstration of that. So let's assume that this is our basis of eigenfunctions. It's complex conjugate. And let's assume that there is another basis and there is a matrix S such that this basis can be represented as a linear combination of the elements of another basis. Okay? So then psi complex conjugate is correspondingly given by this expression. So in quantum mechanics, we often write it in this bracket form, that psi as a vector is a column which includes all these eigenfunctions, is the matrix S multiplied by the column made of this matrix Chi. I think it's Chi. So, and the other way around, if we apply it to the conjugated vectors, which are bra vectors, then we can write it as this vector corresponding to this new basis multiplied by this S dagger matrix, which is a notation for complex conjugate and transposed. Okay? Now, there should be norm invariance when we change the basis, matrix elements between eigenvectors, they should not change. It means that if we calculate the matrix element, the matrix product between the eigenvector psi prime and psi, that should not change. And if we do that, assume that we substitute here expressions, here is for the vector psi, and here for its dual vector, then it will be equal to the same combination of the new basis if this product is equal to 1. This is called a unitary matrix. When the matrix complex conjugate and transposed is equal to its inverse, it's called a unitary matrix. Okay? Probably, if you already done some quantum mechanics, unitary transformations of bases in quantum mechanics is a very common thing. Okay, this is one example. Now let's check that this operation, trace row, it's invariant under this change of the basis. So by definition, taking the trace in this particular basis, it's taking this operator row and calculating its matrix element in the basis psi, okay? Or roughly, because it's diagonal in this basis, so it's will be sum, because this guy is diagonal in the basis, so there is only, this is basically sum, it's a meaning of trace, okay? Now we substitute this psi and psi n in terms of this chi n, okay? Brand cat. And what we get matrix S on the right and matrix S dagger on the left. Now, once we substitute it, we say that the trace with respect to this new basis, chi n, we denote it as trace prime, okay? And that will be of this matrix product. But now, if we replace, if matrix S is unitary, we can replace it by S inverse and write it down as a trace prime S minus 1 rho, but under the trace, you can always move the matrix from the left to the right, and then it becomes SS minus 1 and becomes trace prime. So you see that trace is the invariant operation under the basis. So this definition is basis independent. We started with the basis of eigenfunctions, but now we can choose to calculate averages of our observables in any basis. So the canonical ensemble, as we studied before, when we take the basis, the eigenfunctions of our Hamiltonian, then the corresponding probabilities of being in that eigenstate will be given by exponential of minus beta energy of the state. This is what the canonical ensemble is about. So now we can write this matrix rho. Remember, it's diagonal in the basis of eigenfunctions. And let's, for the basis of eigenfunctions, use this notation of bra and ket vectors. This is a psi, this is psi complex conjugate. And if you know a bit of quantum mechanics, then this is so-called projectors on the state, on the quantum state n, okay? For example, if you remove this factor, then completeness simply means the sum over n, and n is equal 1, okay? But in general, because this is the diagonal element with these entries, here is rho n, so this is any diagonal operator can be represented in this form, and for diagonal entries, we substitute these quantities, okay? Now, we know that En is the energy corresponding to the state n, okay? It means that we can replace it by the Hamiltonian here, because Hamiltonian acting on the state n is just given with En. So we can replace in this exponent, in this exponent, it's with the Hamiltonian as the operator in our hyperspace. Then this factor will no longer depend on n, and we can take it out of the sum, okay? And what's left inside is simply the sum over n, and this is nothing else as a condition of the completeness of the basis, and this sum is equal to 1. So we just derive that the density operator is given by the exponential of minus beta Hamiltonian of our system in our, and H is the operator acting in our space of the system. Normally, it's called a Hilbert space. So, using this expression, we can now write down the average of any observable in any basis as trace of the observable times exponential of minus beta h Hamiltonian. And we need to normalize it by the trace over the diagonal elements of rho itself. And I just showed you that it's simply equal to rho is equal simply to that. Then the trace will be sum over rho n is given by this. And this is exactly the normalization factor which we had in the classical statistical mechanics, but now it's all. So we introduce the quantum partition function as a trace, as the exponential of minus beta our quantum Hamiltonian. This is the major definition of the quantum partition function. Having that, this trace extends over all states of wave functions which satisfy specified boundary conditions. Because if we can impose some specific boundary conditions also in our system, and then we need to calculate the trace only over the space of eigenfunctions satisfying the specified boundary condition. So once we have the partition function, we now can calculate the internal energy by simply taking a partial derivative with respect to beta of the logarithm of that. We can define a free energy of the system by taking exponential minus beta free energy is just equal to the partition function. And we can also write the quantum partition function explicitly now in any basis now, such that summing over all, because that's the trace, summing over all states alpha and taking diagonal matrix element of alpha. Previously, it was this expression we derived when we use as the basis of eigenfunctions. But the basis of eigenfunctions, it's normally very hard to calculate because for that you need to diagonalize your Hamiltonian in the infinite dimensional space. But now this expression is true in any basis. So the only condition that this basis is orthogonal and normalized and complete. This is the completeness condition. So alpha should be any complete or orthonormal set. So now this is what we we've done. We just looked and reformulation of the canonical ensemble, quantum canonical ensemble. Now let's look at the quantum mechanical, or it's quantum mechanical or quantum, because we are talking basically about quantum mechanics, non-relativistic. So let's look at the grand canonical ensemble. With our quantum canonical partition function defined, we introduce now the grand partition function exactly as before. We say that it's the sum over all possible numbers of the particles in the system. Okay, and now let's calculate this grand canonical partition function for quantum, Bose, and Fermi ideal gases. Okay, let me remind you that for these gases, we have, first of all, we count particles based on their occupation numbers of particular energy levels. Then the energy of any particular state is given by the sum over all occupation over levels, and we multiply energy levels by occupation numbers, where energies of individual states equal to this expression in terms of wave numbers, and occupation numbers, they take values 0, 1 from fermions. No more than one fermion can occupy the same state, and infinitely many bosons can occupy the same state. Now let me remind you, why do we want to calculate the grand canonical partition function? Because canonical partition function, if you remember, it's also the sum over all occupation numbers of these Boltzmann factors. But there is a restriction that sum over all occupation numbers should be equal to n. So number of particles in the system is fixed. And then it's in general very hard to calculate this sum with these restrictions. I already explained it to you before when we studied the grand canonical ensemble that restriction basically prevents us to calculate this guy explicitly. When we use the grand canonical partition function, we effectively sum over all possible, over all particle numbers, and this is effectively removes this constraint, and then this sum and this sum will together will be over all non-constrained sequences of occupation numbers, and this we can calculate exactly. So let me remind you how this calculation done. So the grand canonical partition function can be written in this way. So it's a sum over all sequences of occupation numbers with a total number fixed of particles. This is the Boltzmann factor, and this is the fugacity raised to the power capital N. But now because capital N is equal sum of occupation numbers, we simply replace it by Z. Okay? And now capital N, it does not enter here. And so it only enters here. So this is sum over occupation numbers with fixed N, and then we sum over all total number of particles. It's equivalent to removing this constraint, and so the grand canonical partition function is simply summing over all possible occupation numbers in the system. Okay, and this is what we write here. And now this sum, this is z to the sum over sum of all occupation numbers, and here we can split. This we can split into the individual factors. Okay, like z to the power n0, z to the power n1, and etc. and etc. So we can rewrite it as a product of separate sums over n0, over n1, over n2, and etc. etc. And so the whole grand canonical partition function factorizes. And we've seen this phenomenon before, okay? That the total grand canonical partition function factorizes over the product of partition function related to individual energy levels. And now we can calculate these individual sums separately for bosons and separately for fermions. For fermions, this is a really easy sum because occupation numbers, they are either 1 or 0. So there is only two terms in this sum. It's when and no particles, it's 1. When there is one particle, it's simply this one. For bosons, sum runs from 0 to infinity, or this fact. And this is nothing else as a geometric series. So what we get expression with minus here and the extra power minus 1. So as a result, the grand canonical partition function becomes, for fermions, the product over all energy levels of simple factors. For bosons, the product over all energy levels of 1 minus z inverse. Very similar factors, but the power minus 1. And once we know now the grand canonical partition function, we, for example, can calculate the average occupation number in this. And it's simply given as, if you remember before, from the canonical ensemble by this derivative. And if you differentiate this with respect to the corresponding energy, you immediately derive this average occupation numbers for boson and Fermi particles. And that's exactly the formula we derived last time from the semi-classical, semi-quantum arguments about statistics. Now we derived it completely at quantum level. Okay. Now, for the grand canonical partition function, we have the pressure. This is a formula which we derived previously. And now if you use this expression for the grand canonical partition function and go to thermodynamic limit, I will drop this calculation, we get this integral, okay? And then for the density in the system, we get it's sum over the volume, sum over the all occupation numbers. We again going to the thermodynamic limit, and we get this another integral. That's what I called. And when we integrate by parts here, we can easily show that integrating by parts will remove logarithm. It's all the calculation we've done before. As a result, we get this relation between pressure, volume, and the internal energy of the system, which is universal now, and now it's been derived in the quantum for quantum systems. Okay, so the same equation of state, which we derived using from microcanonical ensemble. Now we derive from this quantum mechanical grand canonical. Okay, now the last bit, occupation number fluctuations. It's quite interesting, and I've got about I need about 2-3 minutes to finish. So let's now, with this formula for the occupation numbers, this is a formula how we calculate averages in the grand canonical ensemble. So we normalize by the grand canonical partition function. So this is our occupation number. This is the corresponding factor with fugacity and Boltzmann factor. And then we sum over all possible occupation numbers for the particular level. So if we differentiate it with respect to the energy, then it's really easy to show. We've done this calculation many times before that it will give you the variance. Now, so the variance can be written in terms of the derivative of the average number with respect to the corresponding energy. And if we substitute the expression for the average occupation numbers from here and differentiate it, we get this expression. Okay? And now, if we compare this expression with the average occupation number itself, you can easily check the following equation, that the variance is equal to the average occupation number plus minus average squared occupation number. Okay? It means, and where here plus is for bosons and minus here for fermions. So for bosons, you see that correlations, it's quite a large number. For fermions, remember occupation numbers, it's 0 or 1. Okay? When it's 0, it's 0. When it's 1, 1 minus 1, it's still 0. Okay? So variance, it means that for fermions, average squared occupation number equal to average occupation number squared. There is no difference. But for bosons, we have plus here. So we can write it, if we normalize this variance by the average occupation number, then we can get that 1 from the previous equation plus 1 over the average occupation number. Okay? And that number is greater than 1. So the fractional fluctuations in the occupation number in the gas of thermalized bone is quite large. Okay? And such large, and this is for completely non-interacting bosons. So such large fluctuations were actually observed in the classic experiment of Brown and Twiss in 1957. What they've done, they observed self-interference in a beam of photons emerging from some thermal source. So here is a stream of photons, and here is a semi-transparent mirror. So it divides this beam into 2 equal beams somehow, and then we measure. So it basically means that if we put a detector here at time t plus tau and here the detector t, we can measure a correlation between in the same beam, because they are coming from the same beam, right? So at some distance c tau, depending on tau. This is the typical distance between points where c is the speed of light. And so then we take the product of two intensities at these different points and average over time t. And what was found, that indeed there are very strong correlations with photons. What it means is that photons were found to arrive in bunches. Okay, it indicates that the occupation number strongly fluctuates in time. So Bose statistics enables photons to exist in the same state and in sufficiently large number to produce an electromagnetic wave. So you can imagine it's something like that. So photons, when they're just propagating time, so they arrive in bunches, like bunch here, then nothing here, one, then another bunch here, and then nothing here. They just tend to basically attract in a sense, and they are not equally distributed over time in the beam, but they just somehow arrive by groups. Okay, so this is all for this lecture, and this is the last lecture for this week.